All right, so our next speaker is Gibbs from UCLA, and he's going to be telling us about the impact of flares on short-period brown dwarfs.
All right, is the mic working? All right. All right, my name's Gibbs. I'm a final year PhD student at UCLA, and yeah, I'm going to be telling you about my ongoing work modeling the photochemical and thermodynamic impact of flares on the atmospheres of brown dwarfs that are short period companions to active M dwarfs. And I apologize if my voice gets hoarse during this. Still getting over a cold. So the first thing I was going to say has been covered by quite a few talks already this week, which is essentially that M dwarfs, and especially mid to late M dwarfs, are very active. And those same M dwarfs host a large number of small terrestrial and potentially habitable planets. And that creates this challenge that the atmospheres of these habitable worlds that we'll explore are subject to extreme stellar activity in the past. So a few different groups have done work trying to model what is the impact of that activity, especially stellar flares, on these atmospheres. And this is just one example from Matt Tilley et al. Looking at the impact of large flares and associated proton events on the ozone concentration in an Earth-like atmosphere in response to different size flares. And I think when we're talking about the size of flares, it's useful to have something to compare to. And a good comparison is the largest sort of flare and stellar activity we've ever seen from the sun, which is the Carrington event. So the plot on the left is looking at the impact of ozone in response to Carrington event type flares and proton events. And then on the right are flares of 10 to the 34 erg energy, which are sort of super flares that you can get from active M dwarfs like AD Leo, AU Mic, and others. And basically what they found is that you can have severe changes to the concentration of ozone, for example, or near annihilation for potentially years. But this will be very, very difficult to observe because, one, it's just incredibly hard to observe the atmospheres of terrestrial planets, and especially if the star is active, it makes it doubly hard to observe that. So given that, I've been thinking about what types of atmospheres are the impacts of stellar activity most visible in. Put another way, are there atmospheres that we can observe that are relatively easy to observe that are also subject to extreme stellar activity so that we can potentially look at their atmospheres and tie their chemistry or thermodynamics to that stellar activity? And in the process of looking for good planets like this, I noticed a few systems that look like this. So this is a test light curve of TOI 2119. And what you can see are regular, quite large dips, transits of what is not a planet, but actually a brown dwarf. And accompanying that, you can see highlighted in red large flares. And all of these flares are quite large. All of them are sort of a comparable energy to the Carrington event. And this is not the even most extreme example of this, although it's probably the prettiest one to show. So there's some brown dwarfs on even shorter period orbits around even more active stars. So I think that very naturally begs the question, what will the impact of these flares and other associated stellar activity be? And could this be an opportunity to potentially observe that impact or not? All right, so to find out, I've been working on a modeling project. And basically, I've married two codes together. The first one is neither of these codes I developed myself. The first code is Vulcan, which is a 1D photochemical kinetics code developed by Shengmin Tsai. So this handles the photochemistry given a set number of atoms. It has a dictionary of all the thermochemical and photochemical reactions. And it also models transport by diffusion and vertical mixing in that atmosphere. And so it does the chemistry as long as you have an input stellar spectrum and a temperature pressure profile. And that's where the other code comes in, which is Helios, which is a 1D radiative transfer code, which, given mixing profiles for the atmosphere, determines the opacities and then the thermal profile of the atmosphere. So in working these two codes to simulate flares, they basically work in a leapfrog manner. So just to set up the initial atmosphere, we basically start by running Helios, let it run to an equilibrium, feed the temperature pressure profile from that to Vulkan. Vulkan determines the chemistry, and that feeds it back to Helios to update opacities, and we do this until we reach a steady state atmosphere. And then when we actually apply flares, we have a time-dependent stellar spectrum that both of these codes see, and then again they run in a leapfrog manner, but on a very short time scale that's appropriate for the flares. So we need a time-dependent stellar spectrum, and what I use for that is the fiducial flare code from Park-Lloyd. And this is a relatively simple model. The light curve of the flare looks like a boxcar followed by an exponential decay, which is what you see on the bottom left, compared to a real flare. As the flares get more energetic, their total peak luminosity increases and their duration increases, which is what you see on the top left. And the spectra of this is a 10,000 Kelvin blackbody with an additional UV extension based on the quiescent luminosity of the silicon line. So 10,000 Kelvin blackbody with a UV extension. From other talks, you probably can surmise not necessarily the most realistic, but a simple model of flares. Okay, and the results I'm going to show are for a system that looks like this. So we basically have a GJ832 analog M dwarf. So the base quiescent spectrum is a muscle spectrum. And then we have a brown dwarf at a 20th of an AU. And this is going to be a brown dwarf that's sort of on the hot and heavy side of brown dwarfs. 2,000 Kelvin, log G of 5. And I want to emphasize that this is not really like a hot Jupiter system where the brown dwarf is being roasted by its star. In fact, the thermal profile of the brown dwarf is really just dominated by its own internal energy. The M dwarf doesn't actually contribute a lot to that. So it's not exactly the same as like a hot Jupiter system that you would see. All right. So let's look at some results. So this will be for a 10 to the 34 erg flare, which is like an 80 Leo type flare. And these plots are going to look at the change in the mixing ratio of species compared to your quiescent state over time on the x-axis and with pressure in the atmosphere on the y-axis. So you can see that in the immediate aftermath of the flare, we can have some significant changes in some opacity species. So for example, over an order of magnitude destruction of ammonia, but then actually production of carbon dioxide. Now these atmospheres are pretty hot, so the atmosphere is able to re-equilibrate fairly fast, sort of on the time scale of a day, even from a large flare. A result that I think probably most people would expect: stronger flares, stronger reaction. So this is going from 10 times Carrington to 100 times to 1,000 times Carrington from left to right. And just again, looking at ammonia, you can see the destruction getting stronger and also deeper into the atmosphere. And I think this is what most people would expect. But you can also get some sort of complex behavior that you wouldn't necessarily naively expect. So here's two examples of the changes to, for example, titanium oxide, which can be an important opacity source in these brown dwarfs, which during the peak of the flare can actually be created for a while, and then as the flare ramps down, it can actually be depleted again, and this comes from the balance of two different photodissociation reactions. And then the sort of balance together with mixing can also create different behavior in different layers. So if you look at hydrogen cyanide on the right, there's sort of a layer where there's not much happening with it between two thicker layers that are having some enhancement. And these are just a very short look right around the flare. All right, that was like a high-level overview of the chemistry. So what about the temperature? And I'll say right from the beginning that the temperature effects of even very large flares on a brown dwarf is actually quite minimal. So if you just consider the bolometric absorption of that flare's energy without considering any changes to chemistry, that's what this Helios-only plot on the left is showing. And you can literally only get a change of a few Kelvin to the upper atmosphere from the absorption of this flare. So it's not a significant heating. However, when you couple this with chemistry, with Vulcan, you can get still small, but definitely more significant heating in a very narrow range in the upper atmosphere, and that corresponds to where most of the photochemistry is occurring. So the temperature is not actually increasing there just because of the absorption of the flare, but because of the changes in opacity from the photochemistry. Okay, so I really am an observer, so I'm doing this with the thought of can we observe this? And we probably wouldn't observe these brown dwarfs with transmission spectroscopy, but might be able to actually with high-resolution emission spectroscopy with a large telescope in the near-infrared. So this is simulating the change in the emission of the brown dwarf at a resolution of about 100,000 in the K-band. And you can see that you can get changes in the spectrum sort of on the order of parts per thousand in the immediate aftermath of the flare, and then it dies down as the chemistry re-equilibrates. So I don't think that this is, we have to deal with a star spectrum as well, the starlight. I don't think this is necessarily currently detectable, but I'll also say that there's a lot of physics that's sort of missing in these simulations already, most of which will enhance these effects. I think the most important of which is particle effects. So there could be, larger long-term impacts. So I'll put up my summary and also just say that I'm currently on the job market. So if you'd like to collaborate on similar research in the future, I'd love to chat. Thank you.
You were pointing at me, right? Elizabeth? Okay, cool. Write down afterwards? Okay, great. So Park Lloyd, Eureka Scientific, really cool. I was very stoked to see fiducial flare applied to chemistry.
Thanks.
And I'm curious, so the first slide you showed where you see ozone annihilation as motivation, that is all due to particles that they put into the code.
Yep.
And then you mentioned it again at the end that particles are something that could have additional effects. And I'm just curious to hear if you have plans or ideas for implementing particles in your model, or also known as corpuscles for those of you.
Yes, that's definitely something I would like to do. With this immediate, software framework, I don't know if that's easily done, so I'll probably have to switch to a whole new framework to simulate that. But I definitely think that's important for evaluating these more, yeah.
Thing. Sweet, thanks, sorry. I think this might be a really cool way to turn brown dwarfs into particle detectors, potentially. So would love to chat with you more after this.
Hi, I might have missed it, but I was just wondering, do you have real UV data for which you test your models on? Right,
there's no, well, I'm not sure if there's any UV data for these systems in particular. Me saying they're active is mainly based off just their optical flare activity. So I don't know what the UV environment is exactly, and I'm just making assumptions.
Yeah. Sounds good, thank you.
Hello, Rocio Kiman from Caltech. I was wondering about this brown dwarf that you simulated that is very high temperature.
Yeah.
I was wondering why did you choose such a high temperature, and if you did any with colder brown dwarf, or if you are planning to do in the future?
Yeah, the reason why is that that's actually the estimated temperature of this brown dwarf. And a lot of these brown dwarfs are more massive and relatively hot. That's not to say that there aren't some that are potentially cooler to look at. And there's been other papers that look at like what is the effect of temperature, and usually the cooler atmospheres are more impacted since they don't re-equilibrate so fast.